Alright, this last example, I'm going to actually show you with two different methods. You're going to need to know the Bohr formulas from the last lesson. So again, if this type of question would be providing you with the Bohr energy or radius formulas to allow you to complete the question. But de Broglie's wavelength, by the way, is something that you can derive because you have the momentum of a photon formula. You have the momentum of a particle formula. So in Physics 30, we expect you to be able to put those two formulas together to figure out the wavelength of particles. So the first way I'm going to tackle this one is using Bohr's energy method. And really how you do it really is up to you. The second one just requires you to memorize the one formula I put in your notes dealing with Bohr's average radius. So if we're in the third energy level, that means that this electron, third orbit, it's the hydrogen atom. So what we want to do is figure out what the wavelength of that electron would be. Again, if you're looking for wavelength of a particle is h over mv. So we know the mass of an electron. It's 9.11 times 10 to the negative 31 kilograms. That's not a problem. We also know the charge on an electron, 1.60 times 10 to the negative 19 coulombs. What we need to do is we need to figure out its velocity before we can figure out its wavelength. Well, where do I get velocity from? Well, velocity comes from energy. If I can figure out what the kinetic energy of it was, it'll be equal to 1/2 mv squared. The only problem is I don't know what the energy is, but I can figure it out because I know that the energy of the electron will be equal to the energy level. Back in Bohr, I stated that the energy of the particle in that level is the same as the energy level. So I can figure out E3 using Bohr's formula, E1 divided by 3 squared. So it's a combination of these three formulas that's going to allow us to figure out the wavelength. Before I do any substitution, I'm just going to go walk you through the steps. The third orbit energy level is going to be equal to the electron energy in that level. They're the same value. So if I use Bohr's formula to calculate E3, that'll be equal to the kinetic energy of the electron, which is formula 2, that I could use to figure out how fast it's moving. Once I know how fast it's moving, I could then figure out what the wavelength of that particle is. Quite a series of formulas. The wavelength and kinetic energy formulas can be derived or right off your formula sheet. I would have to provide you, or the diploma would have to provide you with Bohr's energy formula. E1 is a constant. In joules, you would be given this too, negative 2.18 times 10 to the negative 18 joules. So let's start with formula 3. Let's figure out what that third orbit is. Negative 2.18 times 10 to the negative 18 joules divided by 9 tells us that E3 exponent negative 18 divided by 9 gives us an energy 2.42 times 10 to the negative 19 joules. That's the energy of the electron. So going to formula 2, 2 times the kinetic energy divided by mass, square root. You're probably quite familiar with manipulating that formula now. Put that in, 2 times 2.42 times 10 to the negative 19 joules divided by 9.11 times 10 to the negative 31 kilograms. Take the square root. That equals velocity. So multiply your original number by 2, divide by 9.11 to the exponent negative 31. Take the square root of that value, and you end up with a velocity of 7.29. Again, I'm rounding, times 10 to the 3, 10 to the 5 meters per second. Now I'll go to de Broglie's formula and determine the wavelength. 6.63 times 10 to the negative 34 joules seconds divided by 9.11 times 10 to the negative 31 kilograms times 7.29 times 10 to the 5. You should be able to work this wavelength out to be 9.98 times 10 to the negative 10 meters. And if you remember from the notes, the wavelength should be comparable to the wavelength of an X-ray, and it is. You know, 10 to the negative 9, 10 to the negative 10, 10 to the negative 11 will be the wavelengths of these electrons, depending on what orbit it's in. So this is method 1, where I'm using de Broglie's formula, conservation of energy, kinetic energy formula, and Bohr's energy level. The second way you can do this question, which I'll do on the next slide, could be involving the other formula that I gave you in the notes. And again, this would be provided. We are in orbit 3. We know it's an electron. So we could use this formula, 2 pi r equals n lambda. The standing wave part of the notes said that the approximate radius is going to give you the average value. So Bohr actually calculated what the average would be. Even though we know it's a wave-like pattern from standing waves, Bohr's formula came up with an approximation. So the only thing we need to know in here is what R3 is. If you could figure out R3, then you would be able to go figure out lambda. Well, how do you figure out R3? Well, R3 is equal to, again, this is Bohr's formula, R1 times n squared. Well, R1 would be given to you. It's not something you have to memorize. It's 5.29 times 10 to the negative 11 meters. I'm going to substitute, because this is all a little easier to work with, I'm going to substitute 2 into 1, and I'm going to get 2 pi r1 times n squared equal to n lambda. This is a little easier formula manipulation, so I can substitute without doing individual parts. Notice that the n will divide with the n squared, so I can end up here with 2 pi r1 times n equals lambda. A lot easier to do for substitution. So 2 pi times 5.29 times 10 to the negative 11 meters times our n value of 3, and this should give us the same answer, because Bohr did this a different way than de Broglie did, yet they ended up with the same result. So 2 times pi times 5.29 to exponent negative 11 times 3, and we end up here again with 9.9, this one's 9.7, just more of a rounding thing than anything else. These are all rounding values. 9.97 times 10 to the negative 10 meters. these are approximations, right? Bohr's calculation of 5.29 times 10 to the negative 11 is a rounded value. So that rounded value carried through gave us a slightly different answer, but it's to the same magnitude. It's only to 3 decimal places are we finally seeing something a little bit different. So it's kind of neat that two completely different methods on how to determine the wavelength of an electron inside that atom gave us the same result. Bohr did this with his radius formula and approximated his radius using or you could do it with the energy formulas of method 1. Whichever method that you want to choose doesn't matter. This formula would either have to be given to you or memorized, and the Bohr's formulas are always going to be given to you in a question on the diploma. For my exam, you can jot these Bohr formulas down on your formula sheet so that if you do see a couple Bohr questions, you could refer back to them since they're open book anyway.